So let's move to the next talk. So the next talk will be entitled "The DeepFace Generation and Editing with Sketches." So the talk will be given by Dr. Ling Gao. Dr. Gao got his PhD degree from Tsinghua University under the supervision of Professor Siming Hu. And currently, he is associate professor at the Institute of Computing Technology, Chinese Academy of Sciences. His research interests are mainly in computer graphics, geometry, processing, and visual media computing. I think he is kind of like a rising star in our field. And his research contributions have been recognized by multiple awards, particularly recently by Asiagraphics. He received the Asiagraphics Association Young Researcher Award. And let's welcome Dr. Ling Gao. So it's your stage.
Yes. Thanks a lot for the invitation, and thanks a lot for Hongbo's introduction. Now I will share my screen. Yeah. Now let's begin my talk. And today the talk is about the DeepFace drawing and editing using the sketches to generate the face and to edit the face. Creating realistic human face images from sketch benefits various applications, including criminal investigation, character design, educational training. Facial editing also has a great positive influence on the progress of social media and the movie industry. However, it is not easy to achieve excellent face drawing and face editing results. Face image generation is time-consuming. Even for professional painters, it requires more than 2 hours to draw the realistic face images. Besides, face image editing has also high cost. It requires professional software and complicated operations. Existing methods have tried to solve the above problem, such as Pix2Pix could synthesize realistic images from sketches or thematic masks, but it is difficult to generate high-quality results. Photoshop could also edit face image with masks, simple sketches, and colored strokes, but it could not edit facial details like wrinkles. For our approach, we aim to generate high-quality facial images from raw or even incomplete sketches. And given realistic facial images, we could edit the appearance like hair color, skin color, and lighting. Besides, we could also the geometry like facial component and hair structure. First, I will talk about the DeepFace drawing. This is the joint work with Professor Hongbo, Shi Hong, and Shu Yu and Wan Chao. This work is to translate from the sketches to the realistic images, from the freehand sketches to the photorealistic face images. Creating realistic human face images from sketches benefit various applications like the criminal investigation, character design, educational training. Due to their simplicity, conciseness, and ease of use, sketches are often used to depict the desired faces. Drawing face sketch needs professional training. We need first to determine the facial structure and then depict the facial details. When drawing a realistic face image, it is also necessary to considering tone correction. For novice user with little drawing skills, it is hard to achieve such tasks. Could we translate freehand sketches to face image? The recently proposed deep learning-based methods, such as image-to-image translation techniques, allow automatic generation of photo images from sketches for various object categories, including human faces, and this method leads to impressive results. When these methods are applied to the sketch-to-face task, we would get a result like this. This is not good because this synthesized face image exhibits a lot of artifacts. Most of such deep learning-based solutions for sketch-to-image translation often take input sketches almost fixed and attempt to infer their missing texture or shading information between strokes. Since they often train their networks from pairs of real images and their corresponding edge maps, due to the data-driven nature, they thus require test sketches with quality similar to their edge maps of real images to synthesize the realistic face images. However, edge maps are difficult to make, especially for the users with little training in drawing. Users will draw the freehand sketches like this. In our work, we aim to generate a more realistic face images from freehand sketches. Meanwhile, this face image should respect the input sketch. So how to translate freehand sketch into a realistic face image is a very challenging problem. In recent years, conditional generative models, in particular, like the conditional generative adversarial network, have been popular for image generation conditioned on various input types. When sketches being used as conditions, they achieve quality results, only give edge maps as input. Considering the known structure of human faces, researchers have been exploring component-based methods for face image generation. However, their local embeddings learned from real images are mainly used to generate portrait images with high diversity. Conditional generative adversarial networks have also been adopted for the local editing of face images by interfaces either based on the semantic label mask or sketches. Several methods have been made to generate images from incomplete sketches, to synthesize face images from the line maps possibility with some missing face components. Due to their direct condition on edge maps, their solution has a poor ability to handle hand-drawn sketches. Unlike these existing methods, which focus on the sketch-to-image translation, our works cared more about the sketching processing so that the photorealistic image could be generated even from a rough and incomplete sketch. Multiple guidance or suggestions would be very helpful for the user, like this figure. The multiple guidance or suggestive interfaces have been proposed to help users in creating drawings for better quality to provide the corrective feedback based on their input sketch. Inspired by the shadow draw, we provide a shadow-guided interface for users to input face sketches with proper structure, which would be much more easily for users to use this shadow draw guided interface. The key idea of this method is that we use the local to global approach that to reach the local detail synthesis and modeling the shape space of the face components in the image domain to build the sketch manifold. And this manifold will help to improve the robustness of the sketch from the hand-drawn sketches. Now let us go over the details of this methodology in this research work. To train this neural network, it required a reasonable large-scale dataset of face sketch image to sketch pairs. There exist several relevant datasets like COHK face sketch database. However, the sketches in such datasets involve shading effects, while we expect a more abstract representation of faces using sparse lines. We thus contribute to a new dataset of pairs of face images and the corresponding synthesized sketches. We build this on the face image dataset of the Celeb A mask HQ. To extract sparse lines from the real images, we have tried the following edge detection methods. The head method and the traditional canny edge detection algorithm tend to produce edge maps with discontinuous lines. The AP drawing gun is a very recent approach for generating portrait drawings from face photos. This approach leads to an artifact, leads to the although very good pleasing results. However, there are some different from the sketch with the common user. We also resorted to the photocopy filter in the Photoshop, which preserves facial details, but meanwhile brings excessive noise. By applying the sketch simplification method to the result by the photocopy filter, we could get an edge map with the noise reduced and the lines better resembling hand-drawn sketches. We thus adopt this approach to prepare the training dataset, which contains 17,000 pairs of the sketch-to-image pairs. Here is the overview of the network architecture. It consists of two subnetworks. The first subnetwork is the component embedding module. The second subnet consists of two modules, feature mapping module and the image synthesis module. Next, we will introduce each technical module in detail. Since human faces share a clear structure, we decompose a face sketch into 5 components: left eye, right eye, nose, mouth, and reminder. We define the first 4 components simply using 4 overlapping windows centered at individual face components. Here, we treat left eye and right eye separately to best explore the flexibility in the generated faces. To better control the details of individual components, for each face component, we learn a local feature embedding. We obtain the feature descriptors of individual components by using 5 autoencoder networks. Given the input sketch, we could project its individual parts to the component manifold to increase the plausibility. Since the descriptors for different components bear different semantic meanings, we designed the FM module with 5 separate decoding models, converting feature vectors to the spatial feature maps. The resulting feature maps for the left eye, right eye, the nose, the mouth are placed back to the remaining feature maps according to their exact positions of the face components in the face sketch image to return the original spatial relations between the face components. Given the combined feature maps, the image synthesis module converts them to a realistic face image. We use the conditional generative adversarial network, the conditional GAN architecture for this task, which takes the feature maps as the input to generate the realistic image. Here, we adopt a 2-stage training strategy to train this neural network. In stage 1, we train only the CE module by using the component sketches to train 5 individual autoencoders for feature embedding. In stage 2, we fix the parameters of the trained component encoder and train the entire network with the unknown parameters in the FM and IS module together in an end-to-end manner. This method aims to model the shape space of the face components in the image domain. We could use the manifold projection to refine user input sketch at the testing stage. For each component type, the point corresponding the component sampled implicitly define a manifold. However, we do not explicitly learn the manifold, since we are more interested in knowing the closest point in such a manifold given a new sketch face component, which needs to be refined. To verify the local continuity of the underlying manifold, we first randomly select a sample and select one of its nearest neighbors in the corresponding feature space. We then perform the linear interpolation between such a pair of component sketches in the corresponding feature space and reconstruct using the corresponding learned decoder. It could be seen that as we change the interpolation weight continuously, we see that in the embedding space, the semantically similar components are close to each other. We assume that the underlying component manifold are locally linear. Given a new feature vector, to increase its plausibility as a human face, we project these components to the manifold field. We allow the main idea of the classic locally linear embedding algorithm to project the feature vector of the sketched face component to its component manifold. The found component images are then blended as a shadow and placed at the corresponding components positioned for the sketching guidance. We compare this method with 2 other sketch refinement methods, by globally or by locally retrieving the most similar samples in the training dataset. For the easy compare, we overlay input sketches in light blue. The right column shows the corresponding synthesized results. It could be seen that the interpolated sketches almost perfectly fit the input sketches. To assist users, especially those with little training in drawing, we provide a shadow guided sketching interfaces. The idea is inspired from the shadow draw. When drawing, the shadow is displayed under the drawing board, and the shadow is updated instantly for each new input stroke. The synthesized image is displayed on the right. Users with good drawing skills tend to trust their own drawings more than those with little training. We thus provide a slider for each component type to control the blending weight between the sketched components and its refined value after manifold projection. We use the WB subscript C denote the blending weight for component C. The feature vector after blending could be calculated using this equation. Feeding a new feature vector to the subsequent trained modules, we get a new blend synthesized images. Now we show an example of synthesized results under different value. For the female in this training dataset, most of the subjects have long hairstyles. Always pushing the input sketch to such samples would not allow us to create short hairstyle effects. This is solved by trusting the input sketch for its remainder component by adjusting its corresponding blending weight. we can show the figures from the left to right. We must trust the weight, and the hair will be much shorter. This is corresponding to the input sketches. We also do the user studies to evaluate the usefulness and the effectiveness of the system. 10 subjects were invited to participate in this study. Each of them was asked to create at least 3 faces using this system. The study ended with a question to get user feedback on 5 aspects. All of the participants felt that this system was very powerful to create realistic image using such sparse sketches. Also, we put this system into the online manner, so all the users could use this system. And at the last of this slide, we will give the link so everyone could have a try of this system. To evaluate the visual quality and the faithfulness of the synthesized results, we conducted a prospective evaluation study with the result of the globally retrieval and local retrieval. We prepared a set of input sketches containing in total 22 sketches. 60 participants in this study. Most of them had no professional training in drawing. It is obvious that our method gets better response. This video shows the synthesized faces by the participants. It could be seen that this system consistently produces realistic results given input sketches with different style and level of abstraction. We compare this method with the state-of-art method for image synthesis conditioned on sketches in terms of visual quality of generated faces. For fair comparison, we train all the network on the same training dataset, which is the same with our training set. It could be seen easily that this method produced much more realistic synthesized results. Here we show examples of the face morphing using this method. It could be seen that this method leads to smoothly transferring results in identity, expression, and even highlight effects. Traditional copy-paste method using seamless stitching method on colored images. However, there will be situations where the hue of the local area is irrelevant. To address this issue, we combine face components for generating new faces, which could maintain the consistency of the overall color and lighting. And in the DeepFace drawing, we could generate new faces from the sketches. And also, because the sketch is very friendly for the novice users, we could also use the sketch for the user to edit the faces. This is also the joint research work with Hongbo and Chunpeng, Yukun, Rosen, and Shuyu, Liu Fenglin. And in this research work, we aim to develop a method to edit and generate realistic images with the disentangled geometry and appearance. The disentangled geometry is the sketches. We could use the sketch to control the geometry of the faces, and also use the appearance. We could change the faces with other texture. So real face image editing benefits various applications in our daily life. We always want to edit our portrait to make us much more beautiful or much more favorable to have a good impression on other people. However, face editing needs professional training and software. We need to be familiar with the complicated functions of the software and put a lot of time and energy into this software, such as PS. For the new users with little knowledge about the software, it is very difficult to edit the very realistic images, face images by themselves. We already know that the synthesis or generate the realistic images from the sketches have many applications. The recently proposed deep learning-based method allow to generate the hand-drawn sketches from the sketch to the images like DeepFace drawing. However, this method, like DeepFace drawing, is very difficult to infer the appearance information from only from the sketches, because only from sketches we could generate photorealistic images, but the texture and the appearance could not be controlled. While there for only one sketch image, there had multiple corresponding real images with different appearance. So this is the somewhat the limitation of the DeepFace drawing. This method, such as from the sketch to the images, could not control the appearance of the generated images, like the skin color or the hair color. And there are some very related research work. We know that for the generative neural networks, particularly such as the conditional generative adversarial networks, had been very popular for the image generation conditioned on different input types. These conditional inputs, including the semantic mask, which generate good results, but lack of control of the detailed geometry, like Winkler. Another user-friendly interactive model of the geometry control is the sketch. We always talk about the sketch is very friendly, user-friendly. Recent methods could generate photorealistic faces from freehand sketches. However, the appearance plays a central role for the realistic image generation, which is not considered in this sketch-to-image generation method. Recent methods also propose to edit real face images with the guiding sketch, mask, and color stroke. However, these works generate high-quality edited faces with local areas. Our method further supports to edit the faces in both the local and the global manner. Also, this method treats face editing as an image compilation problem with sketch guidance. They could only generate images based on the appearance of the input images, while our approach supports appearance changing from the reference images. Some other methods also propose to disentangle the attribute of real image or specific elements of images, and they do achieve attaching results. However, those attribute-based methods only support editing the specific attributes and could not achieve detailed control. Similarly, the style transform method disentangle the style and content, but also do not support fine detailed editing. This method disentangles the geometry and the appearance of face images and achieves the detailed control of the face generation with sketches or appearance, or the detailed geometry control by the sketches, and also could we change the appearance. The appearance is from the reference images. In this method, firstly, we disentangle the geometry and the appearance of the real images. This method could edit the detailed geometry of the real image using the sketches. Meanwhile, we could change the appearance of the real images based on the reference images. Like the second row of the result, we could change the appearance by some reference images. The key idea of this paper is to design a structured disentanglement framework to support face generation and editing with disentangled control of the geometry sketch and the appearance. We also adopt a local to global approach to incorporate the face domain knowledge. Local component images are decomposed into geometry and appearance representations, which are filled consistently using a global filler module to improve the generation quality. Now, let us go over the details of this methodology, of this method. Here we need to use the paired sketches and the face images to train this neural network. To extract the sketches from the real images, we use the photocopy filter in the Photoshop, followed by a sketch simplification network. And with this paired data, we also need to train a sketch prediction network to extract sketch from wild images for convenience. Here is the overview of the network architecture. We use a local to global approach to process face components individually. This method consists of two subnetworks. The first subnetwork is the local disentanglement module. The second subnetwork is the global fusion module. Next, we will introduce each component in detail. We leverage a local to global framework to generate high-quality face images. Specifically, we decompose a face image into 5 components, including the left eye, right eye, nose, mouth, and background. This is the same operation in the DeepFace drawing, and process them using the individual network modules. Each component has a fixed resolution and is cropped from the real face image. We utilize the sketches to extract geometry information from the real face images. We first train an autoencoder to generate the intermediate features of the sketches. Both the input and output of this network are sketches. Then we train the encoder to map the corresponding image into the latent geometry space of the sketch. For the local disentanglement, both images and the sketches of local region share the space to ensure the correct disentanglement. Appearance is another important aspect of the face image. The mapping between facial geometry and the real face images is clearly one-to-many. But by specifying the appearance, such problem could be solved. Given the appearance and given the sketch, we could determine one face image corresponding to the sketch and the appearance. If we only get the sketches, there would be multiple images corresponding to different appearance. Here we employ another encoder to extract the appearance feature. The appearance encoder leverages global average pooling to element the spatial information. Given independent geometry and appearance respections, an image synthesis generator takes them as input and generates reconstruction or swapping results. We adopt the adaptive instance normalization to control the appearance of generated face images. To train the local disentanglement module, we first train the geometry encoder as described before. Then we fix the weight of the geometry encoder and train the appearance encoder and the image synthesizer generator. During the second training stage, we use a swapping strategy to disentangle geometry and appearance of image. We extract the geometry feature from image 1 and the appearance feature from image 2 to generate a new image. We utilize a geometry loss to constrain it has many geometry structure at image 1. We also extract the geometry feature of image 2 and the appearance feature of generated images. Then we use a cycle loss to ensure it reconstructs image 2. This is the process of the global fusion. To translate the local image features into the complete and nature-looking face image. We take the intermediate feature maps of the local disentanglement module instead of generated images to aggregate more information flow. These feature maps have the same resolution with local input images. Given the feature map of the background component, we replace certain patches of it with the corresponding generated features of other components in the order of mouth, nose, left eye, right eye. Then we feed the combined feature map into the global feature module to generate a new face with desired appearance and geometry. This is the sketch-based interface for the face editing. This is the input sketch overlaid on the top of the geometry image. This is the generated face images. This is the control panel, which consists of some necessary tools such as image opening tools and editing tools. A list of reference appearance images are placed at the bottom of the interface, and you could also load some new images by open the folder. With this user-friendly interface, users could choose some reference images to edit the appearance of the real faces. This method could also utilize sketches to control the geometry of real faces, like changing the contour of the facial components and hair structure. With the geometry of sketches, our method could generate realistic faces with different skin color, lighting, and appearance according to the diverse reference images. So the first column is the geometry. The row is the appearance. With different geometry and different appearance, we could generate this matrix images with the corresponding geometry and corresponding appearance. We also compare this method with the state-of-the-art method for the style transfer. This method disentangle the geometry and the appearance of the image and generate new image by swiping the geometry and the appearance. We could find the result. We could look at this result and the comparison. It could be seen that the result of this method generate much images with photorealistic result and has much better result and with less artifact. We also compare this method with the state-of-the-art method for the sketch-to-image translation. Also, for fair comparison, we train all the networks on the same training dataset. It could be seen that the result of this method, the geometry and the appearance respect well, and also we generate better results in the local region. So in the global manner or in the local detail, this method generates much better results compared with other state-of-the-art methods. We also compare this method with the sketch-based face editing method. We also use their optional editing user interface with the pre-trained model for comparison. Since this method is based on the image compilation, we thus only edit partial sketches. It could be seen that our method generates much better results, especially for the editing task. And also, the editing module in this system enables the user to join faces while coarse or fine sketches. By changing the appearance of the reference image, the realistic face images with diverse appearance could be generated. The user could control both the geometry with hand-drawn sketches or the appearance with diverse references in this system. So we could using the DeepFace drawing to draw the sketches, and these sketches define the geometry, and we use the appearance from the real images, and then the real images define the appearance of the DeepFace drawing results. So also we could use the sketch to editing the existing images. Also, we could to generate some new faces from the DeepFace drawing and use the appearance of other face images to change the appearance. This method learned to disentangle the latent space of the geometry and the appearance in the respective manner and enable the novel application of generating face images with reference of given geometry and appearance pattern. We conduct linear interpolation in the geometry and appearance latent spaces using the corresponding latent code from the given images. The results demonstrate that these interpolation phases are controllable and every interpolated phases have very high validity. Also, these two papers have been published on the SIGGRAPH, and also the fast forward has been selected as the video trailer in the SIGGRAPH conference. And also in the summary, the DeepFace drawing provides an interactive system to produce the realistic face images from the rough and incomplete freehand sketches. And also for the DeepFace editing, the DeepFace editing first disentangle the geometry and the appearance from the images, and then we could edit the sketch and use to combine the edited sketch and the corresponding appearance to generate the new faces. So this is the share some similar technique, but with different motivation and different methodology. And also we open source the code, so the audience could view these pages to download the code. And also for the DeepFace drawing, we also put the DeepFace drawing online. The user could draw by themselves to generate the new faces. We also provide the services. And then firstly, thank the collaborators, thank Professor Hongbo, Shuyu, Wanchao, Rosen, Yukun, and Fenglin. And then thank you for the audience. Thanks a lot.
Okay. Yeah. Thanks, Dr. Lin Gao, for the two interesting works. And let's see. So I got one question. First question. Can we add glasses or?
We should.
Oh, okay. Can you hear me?
Sorry.
Can you hear me now?
Yeah. Okay. I can hear you. Sorry.
Okay. So the first question is, I think it's basically the same, similar to the question to Danny. Can we add glasses or hats to the sketch? Glasses or hats?
Glasses. So because in the training data set we have not faces with glasses, so it's maybe difficult to handle the glasses. But maybe this could, for the potential future work, we could using the data set, adding some glasses to train this neural network. Maybe also we decompose the face image into two layers, one layer about the realistic face image itself, and another layer about the glasses. So I think this needs some special operation.
Okay. And there's one question from a YouTube audience. It's Tong Wu. So he asked basically, how can the DeepFace editing handle side faces or faces with various poses?
Yeah, so this system is not limited to the strictly frontal views. We could handle offset of up to about 30 degrees. And most of the training data set consist of the frontal faces. So large head pose or for the large head pose or for the facial occlusion will affect the disentangle effect. So we could handle some cases, but for the large scale rotation is a challenging cases because they are in the data set there are not so many side view images.
Okay, one more question is from Queen Oliver. So for DeepFace editing, is it easy to edit or change hairstyle?
Oh, this is a very good question. I think this should refer Professor Hongbo's newest work. So we could change much coarse style of the hair, but for the detailed hairstyle, I think Hongbo in this year Asiagraphics Asia provide a much powerful work, especially for the hair. Maybe we can use that word for coarse editing because the DeepFace editing could edit the face detail. It provide a tool for editing the face details and also to edit the hairs in the coarse level. But for the detailed hairstyle editing, I think you should refer to Hongbo's newest work.
Yeah, thanks for promoting my research. And then let me maybe ask the last question. So in the both DeepFace drawing and DeepFace editing, so you adopt a local to global approach. But in Danny's like frameworks, so I think it seems like local to global approach is not necessary for generating realistic or ultra realistic faces. And can you comment on that? Whether it's really necessary to adopt this local to global approach?
I think this may be based on different tasks because we want to generate the faces to corresponding to the strictly corresponding to input sketches. Given the sketch, we need each part of the sketch to each line of the sketch is exactly corresponding to the generated faces. So we need the image translation neural network. We based on that, based on the image translation neural network for the local to global to divide the image into several pages is helpful because we want to train a image to image translation and we divide the image into several patches, we could get much better result for the translation task. And I'm not sure, but from learn Danny's work, they are doing they are not strict, need this strict exact corresponding from the line to the line of the sketches of the line of the images. So without this strict corresponding, so I think mapping or strict mapping, so we would use the style gun or some technique could directly have some good results. I think it's just for this sketching translation task, the local to global is helpful. And for generating the realistic images, it may be not necessary. It might just my understanding is maybe not correct.
Any input from Danny? Yeah.
I'm just saying that, you know, many of the applications, for example, is sketches. I mean, a sketch is only a sketch, so you usually don't really want to be accurate or to be loyal to the exact lines that the user draws. So we have a lot of degrees of freedom. So we need to talk to the artist. I think maybe you work with artists. I mean, what do they want? I mean,
yeah.
I mean, to gain full control or really accurate reconstruction of the edges, my feeling is it's not that important.
Yeah, I think maybe depends on like who your target users are. Maybe for really professional artists, generally I think they would like to have more control. But for casual users, I think since the input is already not that accurate, So I think we could, tolerate more errors in the sketches. But but in PSP work, the local to global approach is not adopted, but generally I think also can lead to quality results. But then the argument is how, the faithfulness of the
question of how faithful you want to be. I mean, what about full body, upper body? I mean, are you thinking about of extending to, I don't know, sketching full bodies?
It's a very good future work, but we are not doing that. But I think it's very useful because now the only faces or head could not be put into the VR environment. If we could sketch the whole body or upper body, it could benefit much VR application. So it's very useful and future research work, and we may explore them. But we are not doing.
I have a collaborative work with students from Swimming Hu, and also Eric is also on the paper submission. But I think it's much more challenge than physics, right? Because of the much higher dimension of human poses.
So we're lucky. We have a lot of work to do. It's true.
Yeah, sure. Okay. I think we have make a full use of the time allocated to us, and then thanks Danny and Ling for the wonderful talks. And I think the talks will be later on. Will be kept at YouTube, I think, for the future audience. And let's wrap it up. That's the end of the second session for Age webinar. Okay, thanks again to Danny and Ling, and then also the audience. Awesome.
And hopefully we meet soon.
Yeah, I hope so. Okay, bye-bye then.
Okay, bye.
Bye-bye.
Bye-bye.